Expecting that you put it where the sun is, it would relax to the circle of Jupiter. Concrete, truly unsteady, and going to detonate. These effects are among the best impacts of radio energy in the whole universe, making more energy than a billion suns. Are you figured out for what will happen? Bug Pound, a gigantic red, very Goliath star, and one of the nearest stars to Earth, has lately gone through a significant darkening that has stood out and mixed feelings all around the planet. This darkening has led to theories among cosmologists and the general public about its natural repercussions. A few experts trust this surprising event could be a precursor to an infinite impact, an overwhelming occasion that happens when a star depletes its atomic fuel and collapses under its own weight, prompting a huge effect. Such an event raises concerns, not just among ordinary experts, but also among the general public, as it suggests questions about the possible impact on our own planet. Scarab Juice is a noticeable star grouping that is easily recognizable in the night sky due to its particular shape and bright stars. Also referred to as Alpha Orionis, it holds the title of the brightest and largest star in this sublime body. Recent data gathered by NASA's Hubble Space Telescope, alongside observations from other observatories, have shown that Scarab Juice experienced a massive mass ejection in 2019. This event is astonishing for a star of its kind and has sparked interest among stargazers worldwide. While coronal mass ejections are a common event in our Sun, the rare occurrence found in Scarab Juice adds a fascinating layer to our understanding of stellar life cycles. Moreover, the distance to Scarab Juice remains a topic of debate among space experts. Some estimates suggest it is farther away, while others indicate it could be as close as 724 light-years from Earth. Determining the precise distances of red giant stars like Scarab Juice is a challenging task due to their colossal size and unique properties. Scarab Juice stands out as one of the brightest stars visible in our night sky, boasting a brightness many times greater than that of the Sun. However, this massive luminosity comes at a significant cost. Scarab Juice burns through its nuclear fuel at an accelerated rate, hastening the inevitable end of its stellar life. Eventually, the star will exhaust its fuel supply, leading to a dramatic collapse under its own gravitational pull, possibly resulting in a massive explosion that could give rise to a neutron star or even a black hole, if our current astrophysical theories are correct. This raises a critical question. Does Scarab Juice pose a risk to Earth? If a tremendous explosion were to occur within a few hundred light-years of our planet, the consequences could be devastating. The impact of a supernova explosion can release an immense amount of light, potentially rivaling that of an entire galaxy. Thus, even if Scarab Juice is relatively far away, the effects of its infinite impact could be significant and far-reaching. Since the last supernova observed in our own system in 1604, humanity has yet to witness such an event locally. However, a notable galactic explosion occurred in 1987 in the Large Magellanic Cloud, located 169,000 light-years away. While that event had enormous implications, it posed no direct threat to Earth, serving as a reminder of the scale and potential impacts of such cosmic phenomena. The concept of a risk zone surrounding an ordinary supernova explosion is captivating and could have serious repercussions for life on Earth. If a cosmic explosion were to occur nearby, it is essential to understand that, in the vast cosmic landscape, nearby supernova explosions are relatively minor events compared to gamma-ray bursts, which are far more powerful and pose a different kind of threat. Gamma-ray bursts can have devastating effects, capable of destroying biospheres and exposing planets to lethal radiation. For example, a particular type of cosmic burst can lead to the destruction of a planet's ozone layer, leaving it vulnerable to harsh space radiation long after the event has occurred. This potential was highlighted in a recent study that outlined new risks associated with massive stars that end their lives in such a spectacular manner. When massive stars explode in a cosmic event, they can achieve some of the brightest luminosities known in the universe. In fact, the brightness of a single cosmic explosion can surpass the combined luminosity of billions of stars. This raises the question of what the consequences would be if Scarab Juice were to undergo such an explosion. If a massive explosion were to occur, scarab juice would become the second brightest object in our sky after the sun. Even during daylight hours, scarab juice, shining brighter than a full moon, would remain visible. The sheer power of the explosion would create a spectacle so astonishing that shadows would be cast even in complete darkness. Such a scene would be both awe-inspiring and terrifying, showcasing the raw power of cosmic events. While the visible light produced by a cosmic explosion is indeed stunning, it is only a fraction of the total energy released during such an event. Although high levels of visible light can cause temporary visual impairment, the greater concern lies in the high-energy radiation emitted alongside the visible light. This radiation often appears as X-rays and gamma rays, which can have far-reaching effects. One of the primary dangers posed by this high-energy radiation is its ability to catalyze the depletion of the ozone layer that protects our planet from harmful solar radiation. Without an effective ozone layer, life on Earth's surface would be exposed to extreme ultraviolet radiation from the sun, potentially leading to mass extinction events. The immediate repercussions of a cosmic explosion present imminent dangers. However, over time, cosmic rays and subatomic particles traveling at nearly the speed of light begin to infiltrate the nearby planetary system. These cosmic rays can deplete ozone layers and coat Earth's surface with harmful radiation, compounding the risks posed by the initial explosion. Furthermore, these cosmic rays carry a significant portion of the total energy released by the cosmic explosion. Their long-term effects could persist for thousands of years. There is evidence suggesting that such events may have impacted Earth in the past. For instance, elevated levels of iron-60, a radioactive isotope produced in supernovae, have been found in ocean sediments and lunar regolith. This finding suggests that Earth may have been affected by cosmic explosion ejecta in relatively recent geological history, possibly within the last few million years. Cosmologists have recently concluded that there are currently no nearby supernova candidates that pose an immediate threat to life on Earth. Based on what we know about the risks associated with gamma rays and cosmic rays, ongoing research has revealed new potential threats linked to specific types of gamma ray bursts, GRBs. These GRBs can produce long-range destructive radiation, posing a more severe risk to planets like our own. The mechanism behind this involves a star nearing the end of its life, surrounded by a substantial disk of material. When the cosmic explosion occurs, a shockwave is generated, striking this disk and causing it to become incredibly hot. This, in turn, produces vast amounts of high-energy X-ray radiation that can travel immense distances through space. The brightest X-ray supernovae have the potential to deplete a planet's ozone layer by as much as 50%, creating conditions that could trigger an extinction event within approximately 150 light-years. Fortunately, no such supernova candidates have been identified in Earth's immediate vicinity. However, this research has led to important insights into the potential consequences of such events. For instance, GRBs are known to produce concentrated beams of gamma radiation that can travel across galaxies. If a GRB were to occur nearby and its beam was directed toward Earth, the effects could be catastrophic. Unlike a typical supernova, which emits energy in all directions, GRBs are highly focused. This means their energy output in a single direction can be immense, amplifying the potential damage to any planets in their path. The radiation could destroy a planet's ozone layer, leaving it exposed to harmful ultraviolet radiation for thousands of years. In addition to these direct effects, the longer-term consequences of GRBs include the destabilization of planetary climates and the disruption of ecosystems. The energetic particles released during such events can alter atmospheric chemistry, leading to cascading effects that may take millennia to stabilize. Despite the potential risks, it is important to note that GRBs and nearby supernovae are relatively rare events. Advanced astronomical observatories and space telescopes, such as NASA's Hubble and James Webb Space Telescopes, are continuously monitoring the universe for signs of such phenomena. Their findings help refine our understanding of cosmic hazards and improve our ability to predict and mitigate their effects. Looking ahead, One of the most critical areas of research involves understanding the life cycles of massive stars like Betelgeuse, often nicknamed scarab juice. By studying their behavior, scientists can better anticipate when and how these stars might end their lives in explosive events. This knowledge is crucial not only for protecting our planet, but also for advancing our understanding of the universe's evolution. In conclusion, while stars like Betelgeuse provide a fascinating glimpse into the dynamic processes that shape the cosmos, they also remind us of the potential dangers lurking in the vastness of space. By continuing to study these celestial phenomena, humanity can gain valuable insights into the forces that govern the universe and take steps to safeguard our place within it. New bits of knowledge regarding the livable zone, the district inside worlds where conditions are ideal for life, have emerged. These discoveries suggest that the habitable zone might depend on additional requirements. Specifically, the outer regions of a galaxy might not have sufficient star formation activity to create the elements necessary for the development of rocky planets. Meanwhile, the inner regions, where stars form and die at a faster rate, pose their own dangers. Ongoing massive explosion events in these areas can illuminate the surrounding space, increasing risks for any potential life that might exist there. New research shows that the inner boundary of the large habitable zone might be farther from the galactic center than previously thought, reshaping our understanding of where life could indeed flourish. So, what will the more chaotic Juice cosmic explosion look like from Earth? While Earth's biosphere will likely remain unaffected, the visual display will be hard to ignore. According to experts, more chaotic Juice will continue to shine brightly for over 90 days following its explosion, reaching a brilliance comparable to a portion of the moon's light, several times fainter than a full moon. Essentially, it will appear as a bright point in the sky, visible even during the day. Its striking brilliance will captivate anyone who looks up, creating shadows even at night. This rare celestial event will undoubtedly intrigue people on Earth. As the cosmic explosion remains visible to the naked eye for some time, its remnants will gradually fade. However, researchers continue to study more chaotic Juice to learn more about the life cycles of massive stars and the processes that lead to their violent endings. Understanding these enormous phenomena is crucial for gaining insights into the evolution of the universe and the creation of elements. During a cosmic explosion, not only is visible light released, but a vast array of heavy elements, such as gold, silver, and uranium, is forged in the intense heat and pressure of the blast. This process, known as nucleosynthesis, plays a vital role in enriching the interstellar medium with the building blocks essential for future star and planet formation. Interestingly, the remnants of a cosmic explosion, known as a supernova remnant, can become a stellar nursery where new stars are born from the dust and gas ejected during the explosion. This cyclical process highlights the interconnectedness of cosmic events and their profound impact on the fabric of the universe. As the remnants of such an explosion gradually disperse into the interstellar medium, they mix with the surrounding gas and dust, enriching it with heavy elements like carbon, oxygen, and iron. These elements, once created in the cores of massive stars, are fundamental for the formation of new stars, planets, and even life itself. Over thousands of years, the shockwaves from the explosion can trigger the collapse of nearby clouds of gas and dust, initiating the birth of new stars and planetary systems. This process is essential to the cosmic cycle of birth and death that governs the evolution of galaxies. The creation of heavy elements during a supernova is particularly significant for life on Earth. Elements like gold, silver, and uranium are essential for various biological and technological processes. These elements were formed in the cores of stars that ended their lives in dramatic explosions. The metals found in our jewelry, the materials used to build our technologies, and even the particles that make up our bodies were all once produced in the hearts of stars. Moreover, cosmic explosions contribute to the distribution of these elements across vast regions of space, ensuring they are available for future generations of stars and planets. In a sense, the death of a star gives rise to the potential for new life. This cycle of star birth and death is a crucial part of the larger narrative of cosmic evolution, shaping the structure and composition of galaxies and planetary systems, including our own. Interestingly, these explosions do more than create new stars and planets. They also contribute to the development of complex structures within galaxies. For instance, the energy released during a supernova can compress nearby gas clouds, triggering the formation of new stars. At the same time, the explosion sends shock waves through the surrounding medium, creating nebulae and other structures that we observe as stunning cosmic formations. These nebulae, composed of gas and dust, are the building blocks for future stars and planets, continuing the cycle of stellar evolution. In the long term, studying cosmic explosions provides valuable insights into the life cycle of stars, the creation of elements, and the formation of galaxies. By observing distant supernovae and analyzing the remnants of past explosions, astronomers can unravel the processes that govern the universe's evolution. Indeed, some of the most significant discoveries in modern astronomy, such as the discovery of dark energy and the acceleration of the universe's expansion, were made through the study of distant supernovae. In conclusion, while the potential for a nearby cosmic explosion like more chaotic juice might seem alarming, it also offers a fascinating glimpse into the dynamic and ever-evolving nature of the universe. The death of massive stars and their subsequent explosions not only shape the structure of galaxies, but also provide the raw materials necessary for forming new stars, planets, and life itself. These cosmic events remind us of the vastness and interconnectedness of the universe, where even the most catastrophic events can lead to conditions for new beginnings. Thus, while the sight of a supernova would undoubtedly be awe-inspiring, it is also a testament to the ongoing cycles of creation and destruction that define the universe. Every explosion, every death of a star, leads to the possibility of new life and the formation of the building blocks for the next generation of stars and planets. As we continue to study these cosmic events, we gain a deeper understanding not only of the forces that shape the universe but also of our own place within it. The story of cosmic explosions and their aftermath also underscores humanity's connection to the universe. Every atom in our bodies, carbon, oxygen, nitrogen, and more, was forged in the hearts of stars billions of years ago. When these stars reached the end of their lives, they scattered their enriched contents into the cosmos, eventually coalescing to form new stars, planets, and ultimately, the conditions for life. This realization, often referred to as Stardust theory, is both humbling and inspiring. It serves as a reminder of our shared origin with the universe and the intricate processes that sustain life on Earth. As scientists unravel the mysteries of supernovae, they not only learn about the distant reaches of space, but also gain insights into the fundamental processes that define existence itself. For example, supernova explosions have helped illuminate the role of cosmic rays, high-energy particles accelerated by such events, in shaping the evolution of galaxies. These rays interact with interstellar gas, influencing star formation and possibly even affecting the atmospheres of planets. Understanding these interactions could offer new perspectives on how life-supporting conditions emerge and persist across the cosmos. Moreover, the study of cosmic explosions has significant implications for advancing technology. The detection and analysis of supernovae rely on cutting-edge instruments, from ground-based telescopes to space observatories like the James Webb Space Telescope. These tools not only help us observe distant phenomena, but also drive innovation in imaging, spectroscopy, and data analysis, technologies that often find applications beyond astronomy. As we continue to explore the universe, new questions arise. Are there other habitable zones beyond our current understanding? Could there be forms of life adapted to the extreme conditions near cosmic explosion remnants? How do the forces unleashed in these cataclysmic events shape the potential for life elsewhere? To answer these questions, future missions and observatories will play a critical role. Projects like the Vera Rubin Observatory and the European Space Agency's Athena mission aim to deepen our understanding of stellar evolution, galactic formation, and the role of supernovae in cosmic history. By probing deeper into the universe, we may uncover evidence of how the cycles of creation and destruction are woven into the fabric of existence. In the end, the study of cosmic explosions is not just about understanding the mechanics of stellar death. It is about embracing the profound interconnectedness of all things. The energy released in these events ripples across space and time, shaping the galaxies we see today and seeding the potential for future generations of stars, planets, and life. Every cosmic explosion tells a story, a narrative of transformation, renewal, and resilience. These events, though violent, are also a testament to the beauty and creativity inherent in the universe. They remind us that destruction is not an end, but a catalyst for new beginnings. As we gaze at the night sky and contemplate the light from distant supernovae, we are not merely observers. We are participants in a vast cosmic drama. Our quest to understand these phenomena reflects our innate curiosity and our desire to connect with the universe that gave rise to us. In this sense, the study of supernovae is more than a scientific endeavor. It is a journey of discovery, one that bridges the vastness of space and the depths of human understanding. By unlocking the secrets of cosmic explosions, we come closer to understanding not only the universe but also ourselves and our place within this grand cosmic story.